And the first one was a quite famous one in, if you look it up in the internet, you will find lots of things about it. Well, the question was, you are going to some game show and then you see there 3 doors, and you know that behind one of these doors, there you are winning the car, and behind the other 2 doors, there is sitting a goat, so you will win nothing. Maybe some of you knows this game show in Germany where you found when you are losing the so-called Zonk. I don't know. You can have a look there. Maybe I will just find some Zonk here. Oops, I am there. As I need in a minute. Zonk, how is he? Does he look like? There he is. Copy, and then again let's go there, and here he is. So what is the situation? Maybe, and here we have our car and door 1, door 2, door 3. Of course, you don't know where you find the car. You only know that the car is behind one of these doors. So then, first round, you choose a door. Maybe number 1. And then the game doesn't end. The quizmaster is not just opening door 1 and you see if you have the song or the car, but now you have a second round. The quizmaster is opening one of the doors you haven't chosen. If you choose one door, then of course you have 3 possibilities. The possibility that you have already the car, then the quizmaster could just open one of the 2 other doors, or you have chosen a song. The quizmaster is knowing that, then he is determined to open one specific other door. And now you are asked, do you want to change your door or do you want to stay at your door? And you are asked if you want to change your choice of round 1. Question. Would you change? Or would you not change? Or the last answer, since we are doing statistics, you can also say, well, anyway, I could flip a coin because my chances wouldn't change if I would change the door. What is your opinion? Or maybe you have already looked it up. Do you change? You change the door. And what is your explanation why you would change your door? Well, you don't know it. Well, this is maybe some situation, but you in the first round, you know nothing. You have only in the first round three doors. One, two, three. You don't know that you are losing with door one. Well, there is many people just argue that they say, well, it doesn't matter if I change or if I'm not changing. And one of the main arguments is quite funny. They argue, well, it is obvious that nothing changes in your probability to win. Nim, take some guy who is flying into the quiz show from outer space, and he only knows, well, it's 50-50 choosing the left two doors, one of them. But actually, you will double your chance of winning when you are changing the door. And the reason for this is what we have talked about. Where is it? Our conditional probability and especially Bayes' theorem. How can we define our situation and model what is happening here? So let's say A is winning the situation that you are winning, and event B would be the door is not opened. And what you want to calculate is the conditional probability of A, I am winning, conditional to what the quizmaster has done in round 2, that the door has not been opened? Well, the not opened door in round 2, this is the door to which you would switch your decision when you are revising your decision of round 1. Well, and this is given to Bayes' law that we have the conditional probability changed P of B conditional on A times the probability of A times the probability of B. Well, what is probability of A? That you choose just one door and you are winning. The unconditional probability that you are winning. 1/3, great. And what is the probability of B that the door is not opened? The quizmaster has a possibility to open one of the left doors. No, not 2/3. He has only two doors left which he can open. You have already chosen the first door, or the door you have chosen in the first round. This one he cannot open. He can only choose between the two left doors. 1/2. So this is maybe the easy part. But now we also need what is the probability that I do not open the door given that this door is winning. Take it slowly. What is the probability that the quizmaster is not opening the door given that behind that door you find the car? So in our example here, when I have chosen number 1, what is the probability that the quizmaster is in round 2 not opening door number 2? Will he open door number 2? Well, if he would open door number 2, would you change then if you see that there is a car? Well, then the game would end. Then there is nothing anymore. Then he just opens the door and yes, you see the car and you say, well, of course, then I'm changing. So in this conditional probability, he is not able anymore to open this door. Because otherwise, there won't be any choice for you anymore if you already see that you are winning. So in the second round, of course, the quizmaster is opening a door where you only see the goat or one of the two goats or the two songs. The door with the car, he is definitely not opening in round two. So what is then the probability? If he definitely do not open, does not he does not open the door. Zero? What is the probability that I'm not opening the door? Just the other way around. It is 100% that it is still closed, okay? Therefore, I meant that you really have to be careful via the argumentation. The event is not opening, given that behind this door you find the car. So the event that I'm not opening is then the safe event, so 100%. But anyway, the discussion went over years in the internet, if you look it up, because the people didn't believe that you double your probability. Because now we just feed in our numbers 100%, 1 times 1 over 3 divided by, 1/2. And this is 2 over 3. Then you're doubling your probability if you change your winning probability from 1/3 in round 1 if you change doors in round 2 to 3 over 2. Yeah, and for this, to solve this puzzle, you really have to careful argument with these conditional probabilities and with Bayes' law. This is one of the central points in statistics, so to speak. Okay, then let's go on. What else did we have? Oh, let's put this within the problem. Here we are. And let's go on. This is the binomial distribution. So then let's maybe let's reduce this in size. Oh, no. Binomial distribution, and let's also take, where is it? The binomial distribution here. let's take the formula and also variance and expected value. So the probability within 10 throws of a dice, you should obtain 3 times a 6. Number 1. What do I have to do? So what we have to do is just to use the formula for the binomial distribution. So what is P, what is N, and what is K? N is 10, great. K, K the number of winning. So to speak, we are winning if yes, K is 3. And what is the probability of a single event that we are winning? What is the probability within one throw to throw a 6? P is, oh, you have it already. P is 1 over 6. So we just insert it. Then P of x equals 3 is 10 over 3 times 1 6 to the power of 3 times 1 minus 6 to the power of 10 minus 3. And let's do this by hand. 10 over 3. What is this? The binomial coefficients. How is it defined? N over k. N over k is defined as if you want, you can also open your microphone and then it will be a little bit faster when we are talking to each other. But I don't know if it's possible. Or don't you know what it is? How it is defined? Okay, then it's n faculty over n minus k faculty times k faculty. What was faculty? This is 1 times 2 times 3 up to times n. So we plug in our numbers. This is 1, 2, up to 10 over n minus k is 7. So 1, 2, up to 7. K is 3 times 1 up to 3. Well, then we see here this cancels out with this up to 8, 9, 10. Here we have also a 2. So this is 3, and 2 is 4. And we have then, if I'm right, please calculate this with me, is 4, 3 is 120. So we obtain 120. Well, this is of course 5 over 6. So we are dividing by 6 to the power of 10, and 5 to the power of 7 is left. Well, this we can type in to your calculator, or I always wanted to do this with Excel with you. So then let's copy this. 527 Let's put this in here, and no, this is not working. Where is it? There we are. To shorten this a little bit. Because here we also have, I think, the binomial coefficients. This is the binomial distribution. No, I don't find this right now. Well, then I calculated this already for you, and this is then roughly 15.5%. And let's just try this. So, first one, how many throws? 10. Probability to win, 1 over 6. This is not the alpha, then I need, I think, word. This one. This one we need. So, number of winning, 10, 1 over 6, and accumulated 15.5%. Here we are. Next one, probability. I think you know this kids game, Mensch ärgere dich nicht, in Germany. And here we want to calculate the probability that you will move out in the first time. And there you remember you have 3 throws, and you can move out when you are throwing a 6. And so the experiment stops. So you are not always throwing 3 times, but you stop the game when you have thrown a 6. So to speak, if you are throwing in your second throw a 6, then you are not throwing a third time. How would we calculate this one? And this is, again, what we have talked about, the situation of independent events. So which number you are throwing in the first time, in the second time, or in the third time does not depend on the result which you have thrown before. Think of this coin flip. Although in an experiment where you have thrown 9 times in a row heads, still the probability to throw in the 10th time also heads is still 50%. Because the 10th throw has nothing to do with the 9th throws beforehand. There we had in the lecture this example of these famous event in the casino in Constance that I think it was 9 times in a row the numbers 0 and 3 has happened. So what is the probability that we are throwing just a 6? No, this is too fast because there you have to think of that you are stopping your experiment. What you are thinking yet is that you always throw 3 times, but you are stopping in between your experiment when you have thrown, as I mentioned it, in the second time a 6, then you do not throw anymore the third time. So let's go through this stepwise. So throwing in the first round a 6 is 1 over 6, yes. First round. So what is the probability that you are throwing a second time? So probability that you throw a second time. This is one event. What is the probability that you not which result in the second time, but that you just throw a second time? 1/2. When do you stop after the first throw? What has to be happened in the first round that you are stopping and the next guy can start? If I have a 6, what is the probability that I have thrown a 6? Oh, sorry, not here, 1/2. This was 1 over 6, sorry. So what is the probability that I do not have thrown a 6 in the first round? This equals the probability not having thrown a 6 in round 1. 5 over 6. Yeah. And then you are throwing the second time. What is the probability that you throw a second time and that you are throwing a 6? These two events, throwing a 6 in the second time and throwing overall a second time, these two events are independent. What can I do with the probability when two events are independent? What is then the overall probability in general? Not now in numbers, but in general. I have event A and I have event B. What is then, if both events winning is independent, what is then the probability that A and B happen? Take the coin flip. What is the probability to have 2 times head when you are throwing 2 times? The first probability is 1/2. The second probability is also 1/2. If the two events are independent, then I can just multiply the probabilities. So it's 1/4, 1/4. Of course, you have 4 different outcomes. 2 times head, 2 times tail, first head, second tail, first tail, second head. So in our case, this probability is 5/6 of, so to speak, event A, and probability to throw a 6 is still 1/6. This is, so to speak, A. This is B. A and B are independent. So P of A times P of B is 5/6 times 1/6. And this is then 5/36. So, and now we ask, what is the probability that I have not thrown a 6 in the first 2 throws? Because only in this situation I'm really starting again and throw a third time. So what is the probability not having thrown a 6 within the first 2 throws? The probability not having a 6 in the first throw was 5/6. What is the probability not having a 6 in the second time? Is of course also 5/6. Both events are independent, so the probability not having thrown a 6 in the first 2 throws is then, using this formula when both probabilities are independent, both probabilities are 5/6. Yes. So this would be then 5/6 times 5/6 is 25/36. So, and now the overall should be that I can move out. So 25 over 36 is the probability that I am throwing a third time. And now the probability to throw then a 6 is of course also 1 over 6 as before. I have still a fair dice. So the overall probability that throwing in the third time a 6 is then 5 over 6 times 5 over 6 times 1 over 6 is 25 over 216. So, and what do I do now? All three possibilities I have, just having a 6 already in the first time, having a 6 in the second throw, and having a 6 in the third throw. What do I have to do then? Overall probability is then, let's say that this is P1 is 1/6, P2 is 5 over 36, and P3 is 25 over 216. So the sum. Great. So 1 overall is 1 over 6 plus 5 over 36 plus 25 over 216 is 36 plus 30 plus 25 over 216 is 80, 91 or? I think so. 91 over 216, roughly 42%. I think you have played as a child this game. Have you known that the probability is almost 50%? Well, actually, this is one of the standard examples. When calculating probabilities, what we have done now or what we have used now is the probability of, where did I had it? Here, the complement, 5 over 6, the complement to 1 over 6, and the, where do I have it? Here, if we are independent, that you just can multiply the probabilities. You never got a 6. Okay. Well, in the end, it's only 50%, so it's also possible not throwing a 6 anywhere. Okay, let's see if we also can do the third one. So you play 4 different statistically independent lotteries. The probability to win is always 20%. What is the expected value and the standard deviation? Well, this is now not throwing a dice, not flipping a coin, but again, a binomial distribution, given that we have n equals 4 and p equals 0.2. So n equals 4 and p equals 0.2. What is then the expected value? Well, not very hard to calculate. N times p. I think you have shown this formula in your introductory course, hopefully. 0.8. And variance, so 4 times 0.2. This would be then the second formula, 0.64, great, equals 4 times 0.2 times 1 minus 0.2, and the standard deviation is just the variance, the root of the variance of x is then 0.8. Thank you very much. So this is A. Then we have B. What is the expected payoff if every success counts 10 euros? 8. Great. And there we are using that the expectation operator is a linear operator. So this is 10 times x, and there we know that we can move out the 10. So 10 times 0.8 equals 8. And number C, calculating the probability to win exactly 2 times. This is more or less the same question as the first one. Again, n equals 4, k equals 2, and p now equals 20%. Putting this in means x equals 2 is 4 over 2 times 0.2, 2 times 1 minus 0.2. 4 minus 2 is 1, 2, 3, 4 over 1, 2 over 1, 2. This times 0.2 to the power, not 0.2, this is 2 over 10. So we have 2 squared over now I'm doing something wrong in my calculation, sorry. Can I write this is then times, now I have it, 10 to the power of 4 times 2 squared times 8 squared, and this is then 3 times 8 is 2 to the exponent of 3 is 689. I think then it should be 2 to the power of 9 over 10 to the power of 4. And this is in the end roughly, I haven't written it down, but then let's take our formula here. And now 2 times winning, 4 times overall, and 0.2 probability is 15.36%. And the last one, number D. Calculate the probability that you lose at least 3 times. What do I have in general then to do? What is the difference to task 3? C, sorry. Hmm? Take the probability of winning once, and what do you also need? What can also happen? Not only winning once, if it's at least lose all time. Yeah, this is a possibility, or the other way around. You say winning 3 times and winning 4 times. Since the binomial distribution is symmetric, it is the same. Well, then let's take the probability overall is then losing 3 times is 4 over 3 times now of losing is the complement probability 0.8 to 3. Then you have to change, or as you said, then you would take 1, 4 over 1 and 4 over 0 with the probabilities exchanged. 0.2 to 1 plus always losing is 4 over 4 times 0.8 to 4 times 0.2 to 0, and this is also roughly 15%. And let's do it also here, that we verify this. That we now need here 3, and the complement probability is 0.8, and a 4 and also 0.8. Oops. This, what I'm doing wrong now is, no, sorry, this is, of course, these two has to be the same, and then we have, sorry, 82%, of course. Okay. Yep. And we have still some time left. What else did we have? I think some integration here. This one we started already, and we have calculated the distribution function that A was 1/2. Let's copy it just up. Where is it? There. And what I want to still have is this one. The rest I do not need. This I do not need. And again, small size. And we have already calculated that we have here 1/2. And that our distribution function then started here and ended at 4. So calculate number 3, the probability that Mike is in between 1 and 2 minutes late at a specific day. Graphically, what do I have to do then? Oh, I need the chat here. Interval between 1 and 2, great. So somewhere here. This area we want to calculate. So do you want to do the integration? So this one, or do you have another idea if we know that we have this linear dependence of our distribution function? What kind of geometric form is our area? What is it? Well, actually, I even don't know if I can just translate this into English. In German. What is the geometric form? I have four corners. Is it just four corners in a very general way? Or is there something special about this geometric form? Yes. Now I have to see if I learned something. Trapez. Okay, no, this is English. This I have to change. So, trapezoid. Okay. And what is the area of a trapezoid? This has actually something to do with statistics, the area of a trapezoid. What is special for, or what defines a trapezoid? A plus B over 2. Yeah, you take the longer side plus the smaller parallel side of your trapezoid and divide it by 2. So you called it A plus B. So let's say this is A, or A and B. So A plus B over 2. What is it called in statistics if you calculate A plus B over 2? Two numbers divided by 2 is, we have talked about this in the beginning of the lecture, in the revision. Sum of n numbers over n is, that is the arithmetic mean of A and B. So now we want to know what is A and what is B. How do we obtain A? So the area is A times B times 1 minus 2. This is your height. Oh, the other way around. 2 minus 1, of course. Sorry. What is A? How do I obtain A? Well, it is a point lying on this line. How did I define this line? Well, I defined it via my distribution function. So this is just f of 1. Inserting this is 1 over 2 minus 1 over 8 times 1 is 4 minus 1 over 8 is 4 over 8. Sorry, 3 over 8, what I'm doing here. And B would be then? Well, you have described it in the right way, but you also have to know how to calculate it. F of 2, yeah, is 1 over 2 minus 2 over 8 is, of course, 1 over 4. Am I right? 4 minus 2 over 8 is 2 over 8 is 1 over 4. So then we obtain 3 over 8 times 2 over 8 times 2 minus 1 is 6 over 64 is 3 over 32, roughly 10%. Sketch the cumulative distribution function graphically. So I'm sorry, you have to integrate. What is the cumulative distribution function? How did we define it? Well, this was just, where do we have it? Here, the integral over the density function. Because then we can say, well, starting from he is in time, 30 seconds late, a minute late, and so on. This is all possible intervals up to, let's say, 3 minutes overall. So the cumulative distribution function is then, let's take this in green, then the area starting from 0 up to, so the cumulative function, if this would be x, then the area is the green area of x. And for this, of course, taking the area, we have to integrate this. Well, since this is just a very simple geometric form, we could also do it via taking a triangle, the area, increasing, but now I want to do it with you with a general dependence that f of x is defined as O to x f x prime dx prime. So then we just insert up to x 1 minus 1 over 8 x prime dx prime. This we have to integrate. What is the integral of this function? The first part, the integral over 1/2. How does it look like? This would be just here 1/2 and a horizontal line up to x. What is this area? X half. Great. So x prime is our variable. There we have to be a little bit careful because in the end we inserting then our limits 0 to x. And what is the integral of minus 1 over 8 times x. This we can split, since we also know that the integral operator is also a linear operator. Therefore, you could move the minus over 8 outside the integration process. So you have only to know what is the integral over x. So you have directly calculated in the right way. Let me still write it down. Integral over x dx is of course 1/2 over x squared. So minus x squared prime over 16 in the limits of 0 to x, and inserting this, of course, inserting 0 is the value of the integral, 0, and inserting x is just interchanging x prime and x. So let's move out 1/2 is x minus, we even can move out the x, would be then 1 minus x over 8. So this is the cumulative distribution function. And how does it look like? You should also sketch it. Capital F x. So a function of the form a plus bx plus cx squared. How do you call such a function? And how does it look like in general? Well, of course, depending, it's broader, it's flatter, it's deeper. The point where you find it in the coordination in your system depends on the values of a, b, and c. But in general, what is this for a kind of a function? And these functions you actually find very, 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 very often in economics. Very often we use linear functions, but then maybe the second most used function in economics is this kind of function. Quadratic function, yeah. This is a quadratic function. And in general, do you know how it looked like? Let's assume c is larger than 0. Then we directly have to argue, since here the coefficient in front of our squared part is negative. Can you describe it how it looks like? Well, maybe you know the name. How do you call the graph of this function? Or think of a and b is 0. This is a parabola. And if you remember, f of x is x squared, then it looks like this. Well, minus x squared is just mirroring on the horizontal axis. And in general, you find then this somewhere there. Well, and this knowledge you can now apply on your function here. And for this, I also rearranged it in this part here because now we know something. We know that the function is 0 at 0. And we know here this is, so to speak, 0 plus 1 half x minus 1 over 16 x squared. And since this is minus, we know that in general our function has to look like this. Then of course we know we are moving here from the left to the right, so we have to be in the increasing part of our parabola. And of course we also know if we are at 4, what has to be then the vertical part? What is the probability that he is 4 minutes late or later? So what has to be the full area of our triangle? 100. Yes, 100%. So 1. So we are here and we know that we are in the increasing part of the parabola, so it has to be look like this. So expected value and variance, 4 minutes. Maybe let's just start. For this, again, we just use our definition. Here we are. So integral over x times density function. Expected value is integral in general from minus infinity to plus infinity f of x prime dx prime. But we know that we are just starting at 0 and ending at 4. So this translates then in O to 4 x prime times, now inserting our density function, 1 half minus 1 over 8 x prime dx prime, and this, I think then it is easier to calculate the integral, is 1 over 2 times x prime minus 1 over 8 x prime squared dx prime. And this would be then, I think this you have already calculated. Integral over x is 1 over 2 times x, so this would be then 1 over 4x squared minus, what is the integral over the second part? Two minutes. We are a little bit in a hurry. So integral over x squared. Which function derived taking the derivative with respect to x is x squared? 1 minute. Okay, how? There are many ways to roam. How did you do it in school? We can do it in another way if you want. Just insert the limits at the point. No, this is not possible now because you have the integration. In the end, when we have the indeterminate function of the integral, then you can insert the limits. So in general, what we now need is to know this integral here. Well, if we take f of x is x to the power of 3, what is then f prime? We integrated the density function, but now we have to integrate x times the density function. And since this is a product, we cannot just use the integration of this one. Yeah? Well, this would be another way. Then you would have to choose the so-called product rule of differentiation. Yeah, here you have this multiplication sign, and integral of f times g dx is not the same as integral of f times integral of g. Yeah. So, but I think you are able to give me the solution of integral over x squared. Yeah, or with the 8 it is x to the power of 3 over 24. And now we are inserting our limits. So this is then 16 over 4 minus 64 over 24. 0 is nothing. And this is then up, up, 4, 6. 6 times 16 is 60 is 96 minus 64 over 24 is 32 over 24 is 4 over 3. So then, homework, variance of x is the integral of now 0 to 4, or let's write it down in the general way, the squared distance with respect to mu, our e of x we have calculated, f of x, oh, x prime, should be careful, dx squared, and inserting this is now from 0 to 4 times x minus 4 over 3 squared and 1 half minus 1 over 8 x dx. Homework. Well, anyway, there are still some tasks left, so then let's meet again on the next Thursday. Maybe it would be nice if you communicate with each other and that you reply me that still somebody is in class, that we do it together. And I really recommend for this lecture, since we are only such a small group, that you really get out something from this lecture, that we are doing the tasks together. And well, this is of course now the revision part, but when we are through these tasks of the first one, then we will do tasks, I think, which are new for you. Because this, I have to admit, you should have already seen in school and in your introductory courses. Okay, then thank you very much for today.